Let us get started with the estimation of the probability density using kernels and use this idea for the kernel regression problem. This will also show and illustrate how radial basis functions can be used towards this kernel regression problem, right. This is an application of RBF towards the kernel regression problem. Okay. So, as I mentioned, can we link RBFs to solve the regression problem? Link RBFs to solve the regression problem. So, let us revisit the kernel regression idea that we dealt a few modules back. So, y of I, which is the observable, is f of xi plus epsilon I equals 1 to capital N, these are the number of samples. F is the unknown function, epsilon I is the random noise, right, for sample xi, and we assume that the noise is statistically independent and identically distributed, independent and identically distributed samples. Y of I is the observable, x of I is a vector, and this is basically our data samples, right. The pair xi yi correspond to the data samples. We can have yi to be a vector as well in a general setup, but since we deal with class labeling problems, typically yi can be some label associated and xi can be a training vector. So, one can think about f as a mapping from some m dimensional space for xi to a single dimensional space, real space, which corresponds to the observable yi. Okay. Now, the question is, what is a reasonable estimate of f? What is reasonable estimate of f? Going in the sequence, we know from basic statistics, if I give you observables y and I ask you what is one reasonable estimate for y, which is f of x, right. Common sense would tell us that let us take the mean, right. If I just want a single quantity that represents this, I just compute the mean and that is my reasonable estimate. So, in this case we look into the mean of the observables around the point x. So, I give you the point x, around that I confine my observation space over a small neighborhood around x to form an estimate of f of x. Now, this f of x is basically expected value of y given x, that is, it is the conditional mean of the observables y given this vector x. Now, we can compute the conditional mean as basically integral minus infinity to plus infinity y times the conditional density, right. This is how we can compute this mean, and that is our estimate for f of x. Okay. This is reasonable. Now, the p y given x can be computed from our joint and the marginal that I know, marginal density that I know for x. So, this term is the joint probability density function of x and y. These are random variables x and y, and this is marginal of x. Okay. X is a random vector and y is a scalar. So, this is how we can compute. Now, f of x which is the regression function. So, bear in mind that this is always the terminology we adopt for the regression function, and if I put an underscore x, it becomes a probability density, and that is the reason why I want to have two separate notations, p for the probability density and f is the unknown regression function. So, the numerator can be computed using the conditional mean, that is what we have, upon p x of x, which is what we have. Okay. So, I think no, I think this has to be erased, because this p x, this is not the density here, wait a second, p x y, f of x is just this integral, not a problem, yeah. So, what we do is f is our regression function. Now, we just compute the integral minus infinity, we have this the conditional density that we need to invoke, which is p y of y given x. Now, what we do is we substitute p y of y given x using this formula here, that is using the joint and the marginal, and we express this out, right. So, this is sort of straightforward. This is from p y of y given x from the conditioning. So, a few points to note: the joint density is unknown, because we do not have an explicit closed form expression for this, and then we may need a non-parametric estimate for this. Okay. So, these are the two important points to note. If you know it explicitly, then you can compute, otherwise you will have to do this using some other estimate. So, let us see how we will simplify the problem. What we do is we invoke the kernel density estimation idea towards solving this problem. Okay. So, just to recall again, so we have these densities that we have here, which we have to estimate, and to estimate these densities we invoke the idea of kernel density estimation. So, what is a kernel to start with? A kernel defined by k of x has properties similar to a probability density function. There are two important properties that the kernel has to satisfy. It is a real valued function of x, and it is symmetric around the origin, where it typically attains the maximum value, and the other property is normalization, that is the area under the surface of this kernel, or I would say the volume under this kernel is essentially unity. Okay. But since we want well behaved functions, we also want to endow these kernels to be continuous, bounded, and these properties, right. In general, just having a real function which is symmetric about the origin may not completely suffice. Good examples of such kernels are the Gaussian kernel. You can also have a cosine kernel, you can have a parabolic kernel, so on and so forth. You can also have a triangle kind of thing, which is a triangle like this can also be possibly a kernel, but it has a sharp this point is basically is not smooth, right. So, we have to basically endow it with two properties, one symmetricity, the other is normalization, and these properties are similar to the probability density function. So, therefore, all possible choice of functions that satisfy these two properties are good kernels for us, right. And one can measure the efficiency of one kernel against a reference kernel based upon some bandwidth and some of the statistical properties. Okay. Now, assuming you have training samples x1, x2 so on till f x suffix n, assuming that we have samples x1, x2 so on till x suffix n, these are all our training samples. We assume that they are independent and identically distributed random vectors, because when you look at sampling the data points from a process, it is a random vector. We do not know what it is. It could be, if it is deterministic function, it is fine. Typically it is not, because the observation noise can make it random. Plus in general these examples themselves, exemplars or these feature vectors, they themselves could be random. Okay. The Parson-Rosenblatt density estimation of Px of x is given by this quantity P suffix x, capital X of x, the hat, which is an estimate. So this is basically a PDF estimate, is given by this equation 1 upon n times h power m naught, the summation I equals 1 to capital N, this kernel function k evaluated at x minus xi upon h. Recall again that xi is the data point and x is some continuous random variable. Okay. There is this parameter h here, and this controls the size of the kernel, or in general the bandwidth. X and xi are vectors in an m naught dimensional space. So therefore this PDF is essentially in a multivariate PDF, and this h is basically a scalar quantity which is controlling the bandwidth. Now one might question, what is the role of h? How do we choose h? Right? Typically h can be as small as possible. If it is as small as possible, then we get a sort of a fine tuning there, but if h is large, you can imagine that it can accommodate more data points. So there is a sort of natural bias variance trade off that is happening via this parameter in the estimation of the density, right. If it is shrinking towards a delta function, the bias on this would be there, but the variance is not there. But if you involve some sigma, then I think there would be variance. So therefore this parameter h can control the bias variance trade off. Okay. Now if h equals h of n is a function such that the limit as n goes to infinity h of n is 0, then the expectation over this estimate of the density function that goes towards a true density of x, and the bias is not there. I mean this quantity limit of something, limit of the expectation of this estimate minus p of x, if this is 0, then the estimate is asymptotically unbiased. Okay. This is an important property. So for this to be satisfied, then this limit as n goes to infinity h of n should be 0. Now let us formulate the Parson-Rosenblatt density estimation for the joint PDF. So if you recall, when we had to compute the conditional mean, we required the knowledge of the conditional density, that is probability of y given x, is what we required. To compute that density, we had to do the joint over x and y upon the marginal of x, right, the density which is basically the marginal density of x. So, let us see how we can use the kernel density estimation idea towards this purpose. Okay. We assume these pairs x y are independent and identically distributed. Okay. This is a reasonable estimate. So, therefore, the estimate of the joint density joint density of x and y is given by this quantity 1 upon n power h power m naught plus 1. So, why you have the exponent m naught plus 1? Because x is an m naught dimensional vector and y is just belongs to R, right. So, it is in single dimension. So, therefore, the dimension is what we have to scale here. So, it is going to be m naught plus 1. Now, this is going to be summation I equals 1 to capital N, the kernel acting on the points x and the kernel acting on the points y. So, the same idea, x minus xi upon h, k acting on this, and then k acting on y minus yi upon h. Y is a scalar, yi is the data point which is the observable, xi is your feature vector, and x is this continuous variable. Okay. Now, we can estimate the joint in this form, and we know how we can estimate the marginal because we wrote how we can do the estimation. So, now we are almost there to simplify this problem. Now, what we need is the following: we need to compute this term, which is integral minus infinity to plus infinity y times the estimate of the joint, right. That is how we started off with equation number 1. So, if you just recall equation 1, it was integral of this quantity upon the p of x, which is the marginal of x, okay, marginal density of x. Now, we have the estimate p x y, this is given by our previous slide here, we have this estimate here. So, we plug this in into this quantity. So, this boils down to basically computing this integral, this is summation I equals 1 to n, this is a scale factor 1 upon n power 1 upon n times h power m naught plus 1 times summation I equals 1 to capital N, this kernel acting on the data point x times this integral minus infinity to plus infinity y times the kernel acting on y, which is y minus yi upon h, right. We need to compute this integral, still looks sort of messy, right. Now, fortunately we can simplify this. So, we have to simplify this integral. So, let us compute it. Let us compute the integral. Now, what we have to do is basically define a new variable z, which is y minus y sub I upon h. So, we just make a change of variable here. So, y is basically y suffix I plus z times h. So, dy is basically h times dz, because this yi is derivative is 0, it is so it is going to be h times dz. Now, we plug this back into this equation here, this is integral, we plug this into this equation into this expression integral minus infinity to plus infinity y times this kernel dy. So, what we get is yi plus zh, plug y here, just drop in y here, times k of z into dy is basically h times dz. Now, we pull this h outside, we have two terms in this braces. So, we just break this integral into two terms, we expand this integral out. So, it is basically integral minus infinity to plus infinity y suffix I k times k of z dz plus integral minus infinity to plus infinity zh times this kernel k of z dz. We have two terms. Now, the reader or the student can see through very clearly why we want to invoke the two properties of normalization and symmetricity, right. So, the first property is invoking the normalization. So, y suffix I is basically a constant, you pull this out of this integral, it is k of z dz, and integral of this kernel essentially is going to be 1. This is a normalization property, right. So, this basically evaluates to 1. So, yi is pulled out, and then let us look into term 2. So, basically h can be pulled out and we have z times k of z, and that can be interpreted as the mean of this kernel, right. It can be interpreted as the mean, and the mean happens to be it is symmetric, and therefore, you can basically evaluate that integral to be 0. Okay. Now, term 1 evaluates to y suffix I because of this property, this is normalization, and this integral happens to be 0 because it is symmetric, and we can assume it to be 0 mean as well. Now, what boils down here is this integral minus infinity to plus infinity y times this joint density can now be simplified. So, 1 upon n power h power m naught plus 1 is what we have. So, by plugging these values, term 1 is 1, term 2 evaluates to 0. So, we have a scale factor h sticking out of term 1. So, we plug that in, and we also have this y sub I which also comes out of this integral. So, we pull this out. So, all we have is this equation here, which is basically this quantity 1 upon n power h power m naught plus 1 times h times this summation I equals 1 to n y suffix I, the kernel evaluated at x minus xi upon h. So, there should be a vector here. Okay. Now, we are almost there. Our regression function, which is evaluated as the expected value of y given x, which is the conditional mean, can be simplified in this form, right. This was our original equation, just sort of recalling this where we started off, and then we plug in for the estimate for p of x y, which is the joint density, and then p of x, which is the marginal density of x, and we arrive at a compact form. So, this is basically summation I equals 1 to n y suffix I, the kernel evaluated at x minus xi upon h upon summation I equals 1 to n, the kernel acting on x minus xi upon h. Okay, this is a compact form. So, all we need is data points xi and corresponding observables y suffix I. So, given this with some function k that we start off, we can compute the regression function. Okay. You may also wonder, does the denominator term evaluate to 0? It does not, because it is a valid density, it is basically non-zero, right, because it is acting on these points x of f x suffix I, it is basically non-zero. So, everything is sort of valid in the expression that we have derived for the regression. Okay. Now, there is also this estimator, which is sort of well known in the estimation theory community, which is the Nadaraya-Watson regression estimator. Let us define the normalized weighting function to be w n comma I of x. So, n is the number of data points and I is for the ith sample. So, the normalized weighting function is defined as this quantity, the kernel acting on x minus xi upon h upon the summation of all these kernels acting over different data points xj, j going from 1 to n. This is normalization, and you can straightforwardly verify that the summation I equals 1 to n w n comma I of x is 1. This is very straightforward. You put a summation here on the left hand side of this equation, on the right side put a summation there. The denominator is basically constant, you can pull this out, and then when you sum this over all I, the numerator and denominator cancel out and it is just normalized. So, that is why this is called a normalized weighting function, that weights, it provides a weight to the ith data point, right, it provides a weight to the ith data point xi. Now, once we define the normalized weighting function, given the weighting function and the observable, we can compute the regression, the regression function. Okay. So, it is straightforward. The regression function f reg of x is given by the summation I equals 1 to capital N, the observable y times the weighting function associated with that observable that depends on the data point. So, I write it down in this form, it is summation I equals 1 to capital N, this is the weight and this is the observable, and this weight depends on xi, because this is a weighting function for the point xi. So, we have made use of both the pairs xi and yi, that is each data point comprises of two coordinates xi and yi, xi is a vector and yi is the corresponding observable. So, given these 2 points, we invoke the kernel and then we formulate the regression estimate. Okay. So far I have sort of given you an idea how to do this kernel, using kernels how we can come up with our regression estimates. But what is the role of radial basis functions? Why are we bringing this in this topic, right? You may be even pondering about this. The radial basis functions use Gaussian kernels, right? You can use, generally you can use any other kernel, but typically we use Gaussian kernels and they have radial symmetry. Okay. So, now we can use RBFs, which is radial basis functions, towards the regression problem. We will see this in a while. Now, the kernel in the RBF has spherical symmetry. So, the kernel acting on x minus xi upon h is equivalent to writing kernel acting on the norm of x minus xi upon h for all the data points or all the pairs of data points xi yi, right. Now, this norm is the L2 norm, which naturally provides us with radial symmetry, right. Let us define psi n of x comma xi like the way we define the weighting function in this form, which is kernel evaluated at norm of x minus xi upon h divided by this summation j equals 1 to n of this kernel acting on all the points. So, this is sort of like the weighting function that we discussed in our that we discussed during the NWRE estimator. Okay. Now, we take this one and we plug this in to our regression function. As usual, this normalization this weighted the normalized weighting function sums to 1, that is summation I equals 1 to capital N of all the weighting functions, this sums to 1, and the regression estimate is basically a weighted sum. This is very very important, is basically a weighted sum of n basis functions given by psi n of x comma xi, right. And you can treat this like this. F reg of x is basically summation I equals 1 to n w sub I psi n of this. So, it is a different way in which you can interpret. So, here you can say that the weights are like your observables and psi n are basically the basis functions, right. So, this is a sort of a interpretation using weighted basis functions. These are like our basis functions. I will put these letters RB standing for radial basis. They are our radial basis functions which are computed for every data point xi, and this is the weight, and this can be interpreted as a weighted sum of n different basis functions, and the weights are essentially the observables. Okay. So, this sort of completes our regression estimation formula. There are a few points to note. So, one is with the RBF regression estimation. If you look into this quantity A, right, this equation f reg, this denotes input output mapping of a normalized radial basis function where these functions are between 0 and 1. This is an important note. And this quantity psi n of x comma xi, which you call this as a basis function, can be interpreted as a probability of an event described by the input vector x conditioned on xi. Right, though it is a function of x, but if I give you an input vector x and a condition on xi, then I can interpret this as a probability. You would also note that the density estimation problem can be ill-posed. So, you may wonder what is this ill-posedness and how can this occur. Now, is there a unique solution for our regression given these points? what is the right way to choose these weights? So, these are the problems that one may ask, right. We will get into this notion of well posedness and ill posedness when we begin our journey into regularization theory, but if you are savvy to think about it at this point, you will wonder what is the best way to choose these weights, how can we optimize them, given the data points, is it sufficient, are we an underfit, are we an overfit, these questions you get, for which we have to study regularization, and this is an important subject topic for a module that we will study later, right. So, we can constrain the set of variables and parameters that we have, put additional constraints and optimize a functional along with the constraints, and that gives us a solution towards our parameters that are unique and that can describe this problem well. Okay. So, we will stop here and we will continue with our discussions on this when we touch upon regularization.